Hey there, I'm Tyler Trott, and this is my reading summary 4 for Federated Learning through Model Gossiping in Wireless Sensor Networks. Firstly, a brief introduction of the ideas discussed in this paper to build a foundation of understanding. Federated learning is proposed as a decentralized mechanism using the on-device processing capabilities and the collected data to train the model in a distributed manner. What this means is that each member of a federation, a node in the network, of the distributed learners trains its models locally using only the data it possesses, and then sends it to another node that is in charge of transmitting it to an aggregation point or elsewhere. This is then sent back to the original sendee for further training and use locally. More on this later. A fun example of FL that everyone knows of is the Hey Siri vocal classifier feature with Apple machines. Each phone exists as its own node and updates its model around its owner's voice and speech patterns, sends this information to Apple. Apple updates the global model and sends the updated model back to the phone. Gossiping is a mechanism that allows for a set of nodes to exchange local information such as measurements and/or model parameters to reach some global or partitioned consensus regarding such information. The paper proposes an idea of integrating this mechanism into a federated learning network to potentially reduce the number of transmissions needed to be sent in total. This would lead to system performance concerning energy consumption, network lifetime, and network overhead, as gossiping was initially conceived to solve the consensus problem by exploiting resources at each node to decrease the amount of data that needs to be transmitted. The objective of gossiping in a WSN is to allow all nodes to share some estimation of the average of models that exist in that network. The overall arcing issue that this paper is attempting to tackle, as aforementioned, is that FL algorithms cannot be integrated seamlessly into WSNs as they require large numbers of transmissions of model parameters given the frequency of naturally distributed datasets that continuously update. This process of transmitting this information results in huge energy and communication resource consumption, especially at nodes physically closer to the point where the information is aggregated. More on this later with the proposed solutions. WSNs are self-explanatory, I hope, considering the audience of this video. So let's not dive too deep into that. The paper's overall solution to the issue revolves around integrating the gossip mechanism combined with an FL algorithm so that a higher energy efficiency and bandwidth saving is achieved. The results, which are provided within the paper, show that gossiping can, in fact, assist in improving performance in terms of resource efficiency. At the time this paper was published in 2021, it was stated that FL implementations had not exploited the capabilities of the multi-hop paradigm. This paradigm is simply when devices communicate over multiple hops or relays to reach a destination outside their direct communication range, rather than relying on a single direct connection. The paper goes on to explain that FL aims to solve the distributed learning optimization problem mathematically. The minimum number of parameters from the global loss function. The global loss function is denoted as the summation from k equals 1 to the total number of nodes of pk, denoted later, and the objective function of a local node and its parameters. F of w is the objective function, also known as the global loss function. For those of us that are either unfamiliar with machine learning or are a bit rusty, the objective function considers the entire dataset, or a large portion of it, when determining the model's performance and guiding its training. It aims to find the best overall model parameters to use. W is the vector that contains the model parameters. K is the number of network nodes. PK is the weight of the kth learner such that the summation of all PKs of the collection of nodes equals 1, the proper weighted average. This is pretty much seeing how much influence the kth node has on our objective function. It's important to note that nodes with more training data have higher, something alpha, I assume. If devices have equal PK, then each learner has an equal impact. This is a highlight as I'll be mentioning this later. Now that we know this, we can review one of the proposed solutions from the paper. Instead of all nodes communicating directly with the aggregation node, which is common in originally architected FL networks, the paper proposes a multi-hop approach where nodes send updates to their parent in a spanning tree. Parents aggregate updates before forwarding them up the hierarchy. This reduces the number of direct transmissions to the central node, which alleviates some of the stress these nodes used to work under. Additionally, the gossip-based algorithm they utilize in this paper prioritizes nodes with better models so that they have a higher probability of broadcasting their updates. With this selection prioritizing better models, it reduces redundant updates. And compared to traditional FL, this approach aims to reduce bandwidth usage and improve scalability. Reducing direct transmissions to the aggregation node helps scalability by minimizing the communication overhead, reducing network congestion, and lowering latency. Potentially. However, I believe this method introduces potential biases and computational burdens. Firstly, yes, I believe this strategy reduces stress of the aggregation node. However, this solution can potentially shift this workload and overhead onto parent nodes that possess a high number of children. On top of this, this introduces a potential flaw for failure points. If a parent node fails for any reason, its parameters and values are lost in addition to the parameters and values transmitted by its children. With the failure of this parent node, the children also lose their path to the aggregation point for as long as that node is not functioning or transmitting information. I can also see a potential issue for latency for nodes that have longer paths and more hops than others may have, which can lead to straggler effects given the fact that some parent nodes may take significantly longer than others to transmit the aggregation node. Looking at this solution in big O notation, we are also functionally changing our performance from O of 1, since nodes transmit directly to the aggregation point, to O of n, where n is the number of hops a packet needs to commit. We also don't actually know what the distribution of nodes looks like, given that it can exist in any network. Something that can be integrated to mitigate the risk, I think, could be balancing the trees of nodes or implementing some type of adaptive structuring. But this would be extremely expensive, depending on the size of the network itself. Something else that I think would be important for this proposed solution is introducing redundant pathing, such as backup parents and alternative paths for child nodes to prevent absolute loss of information in the event of a parent node failing. One last talking point I wanted to note was the type of gossip algorithm the paper utilizes. They are using randomized pairwise gossiping. Essentially, each node K possesses some estimate of the model parameters, WK, which are initially obtained by training the model using local information only. Let WIT denote the model parameter at node I at iteration T. The node broadcasts this model to all neighbor nodes in a similar fashion of short-range flooding of the network. Let J denote the node in radio coverage of I. When J receives a message from I, it updates its model accordingly. WJT plus 1 equals alpha times WI of t plus 1 minus alpha times WJ of t, where the parameter alpha is denoted as the interval between 0 and 1, which measures how much the receiving node weighs the received model in comparison to its own. What this means is that when a node receives a model, it compares the value of the loss function, how well or how poor it performs, of the received model and compares it with the value of its own local model. Recall that the paper implemented an algorithm such that nodes with better models are more likely to broadcast it. So, in the scenario where the achieved loss from another model is less than the current local model of a node, the node updates and retains the received model and then uses its own parameters on the new model. The paper goes on to show, in addition to being backed by the analysis done by A.G. Demakis and others et al., that with gossiping, each node is guaranteed to converge as long as the network is continuously connected or possesses at least a considerably high uptime. Albeit, convergence may be slower given the size of the network, because again, we just don't know. Talking about the size of the network, this algorithm is great for working well in large scale networks without requiring a centralized coordinator, on top of reducing the number of direct transmissions, as was the original issue the paper wanted to resolve. However, the setup of this algorithm, I believe, can introduce skewed model dominance, in other terms, node bias. If a node, or even a set of nodes, has higher alpha levels than the rest of the network, their models are and can spread more frequently. This can lead to an over this can lead to an overrepresentation of certain data distributions. The other nodes with different but equally important information might be ignored or not utilized as frequently as they should be in the system. On top of this, the nodes with higher alpha levels create a strange rich get richer scheme and feedback loops. Because if a model is presented as high quality, it stays as high quality and can even increase in quality over time, leading to the frequency of its utilization to also increase over time. It's important to also note that the location can impact models as well. As an example, for my project of urban traffic optimization, if I were to implement this proposed solution, I would expect my system to find that models that exist in intersections that possess higher volumes of vehicles, like any urban intersection, would have a lower alpha level given the wide range of variation. All the while, in suburban rural areas, the alpha levels would be much higher, given the fact that the volume of traffic would be considerably less and more predictable and easier to compute manageability. The models that would exist for these suburban rural areas would absolutely not be worthwhile to have in urban areas, especially in locations such as downtown intersections. We all know how bad Douglas is. Also, a quick side note, I think it's important to not have some nodes ultimately ignored or utilized less frequently, as these nodes may possess edge cases or rare scenarios, such as higher volumes of emergency vehicles, depending on the location. There may be a hospital around, or maybe a fire, police station, etc. Some potential improvements for this proposal of an algorithm would be to actually adjust the alpha value dynamically and not be solely dependent on model quality. It would be good to use a diverse range of nodes to distribute models somewhat equally. It'd be important to monitor underrepresented nodes in these networks and try to take into consideration the reasons for the underrepresentation in the first place. You can also set a minimum participation guarantee. This could look something like the following, where for every n rounds or iterations, you can force a synchronization on all of the nodes so that they all contribute to some agreed upon aggregation point, or even a collection of aggregation points that aggregate at a later step so that all nodes can contribute equally. This paper presents, I'm getting lost in the sauce here. One second. This paper presents a promising multi-hop and gossip-based FL approach, improving communication efficiency in WSNs. However, it introduces bias, failure sensitivity, and computation bottlenecks that I think must be addressed. By implementing fair aggregation strategies and redundancy mechanisms, FL and WSNs can be made more robust and scalable. Thanks for watching. If you have any thoughts or maybe alternative solutions, feel free to share them in the comments on Teams. Here are the references that I used for this script. Yes, this was scripted, I promise. This wasn't just a free-for-all. And I need to go back and edit the rest of this. So let's go. I think that went fairly well. Thank you.